Welcome back to this explainer by Forge College. I'm absolutely thrilled to have you here. Today we're making a big shift. We're moving from the architectural blueprints we drew up in our last lesson, Integration Design Review, and we're actively machining our concrete security components. Now, this explainer covers the capstone, comprehensive access control system, which sits right in the heart of access control patterns and Solidity within the applied Solidity development track. Basically, this is where the rubber meets the road, or, where the code actually meets the blockchain.
So, let's take a quick look at today's schematic. We're going to forge our integrated access module step by step. We'll start with a contract blueprint, build out the master key, install an emergency panic button, mint some security ID badges, wire all those defenses together, and finally wrap up with quality assurance and testing. It's a packed assembly line, so let's just dive right in.
First up on the bench, Section 1, the contract blueprint.
All right, let's lay out the basic skeleton of our smart contract. We're building a reusable contract module named Integrated Access. Think of it kind of like the foundation chassis for our entire security system. But before we pick up the welding torch, we really need to understand our primary tool here, the internal helper. In smart contract development, an internal helper is essentially the actual physical lock mechanism in our code. It's just a centralized, reusable function that performs a very specific logic check. And the beauty of this, it keeps our modifiers incredibly thin, gas-efficient, and super testable. We absolutely don't want bulky, complicated gates on our functions. We just want sleek, modular locks that do one thing perfectly.
Moving right along to Section 2, building the master key.
So the very first concrete component we need to assemble is this master key. This is your ultimate admin access. It focuses strictly on setting up owner-level access control, and we're going to assemble it in 3 straightforward steps. Step 1, we assign the deployer as the owner right inside the constructor when we deploy. Step 2, we draft that internal check owner helper function we were just talking about. It simply makes sure the transaction sender is actually the owner. And finally, step 3, we attach our only owner modifier to the door. This acts like a bouncer that calls our internal helper. By separating the logic out like this, our test suites can call those low-level checks directly without having to jump through a bunch of syntactic hoops. It's just so much cleaner.
All right, on to Section 3, the emergency panic button.
Look, we all know that sometimes, despite our absolute best efforts and planning, things just go sideways in Web3. You've got to have a way to stop the gears from turning. Interestingly enough, we built this emergency panic button using a simple pause toggle and a when not paused modifier. By sticking this pause check super early in our execution stack, we guarantee that we're not wasting precious gas doing complex role lookups or state changes if the whole system is under lockdown. It isn't just about safety, It's about network efficiency and preserving your contract's core invariance when things get chaotic.
Next on the line, Section 4, minting security ID badges.
Okay, so obviously not everyone needs that master key we just built. Some users or even external contracts just need access to specific rooms. So here's exactly how we construct that delegated access. First, we define specific role identifiers, like a pauser role hash. Then we create a has role mapping check to verify if an account actually holds that specific badge. We build functions to grant and revoke roles efficiently, and finally we draft a check role internal helper. Now, as we always emphasize across Forge College's learning programs, you have to be incredibly careful here to avoid redundant state reads on the blockchain. Role lookups are 2-slot mappings, so we use our hasRole function to read the state exactly once per check. Think of it like checking an ID badge once at the front desk instead of checking it again at literally every single office door down the hallway. Saves a ton of time and gas.
Bringing us to Section 5, wiring the defenses together.
This is the crucial part. We're taking these individual locks, buttons, and badges and wiring them into one seamless defensive perimeter around our smart contract. And this brings up the concept of the composed modifier, which really just means stacking multiple modifiers onto a single function to enforce layered, sequential access control. By stacking them, we're basically creating a highly secure hallway of consecutive gates that users have to successfully pass through just to execute their code.
But this brilliantly illustrates a classic engineering trade-off. In what order do we stack these gates? Do we check the panic button first, which fails fast and saves the user gas during a system lockdown? Or do we check the user's ID badge permissions first, which gives us much clearer revert error messages for easier debugging? Well, in our capstone architecture, we generally put the pause gate first to stop execution as early as humanly possible. Take a look at this beautifully clean schematic. It maps our protected functions to their strategically applied security gates.
A critical action requires you to pass the when not paused gate and then immediately pass the only owner gate. Meanwhile, a delegated action passes the when not paused gate, but then only needs the only roll check for that pauser roll. It's neat, it's sequential, and for sure, it is highly secure.
And finally, Section 6, Quality Assurance and Testing.
All right, the machinery is fully assembled, so it's time for QA. Because let's be honest, we all know a compilation failure is really just your computer's way of politely asking for a missing semicolon. QA starts with running our local compiler, whether you're a hardhat fan or a Foundry user, just to check our basic syntax. Then we run lightweight behavioral checks to guarantee every single lock and alarm functions exactly as drafted. We verify that calling an owner-only function from a non-owner address actually reverts. We verify our role restrictions are tight. And critically, we verify that toggling the pause button completely blocks all protected actions across the entire board. As we wrap up this phase of construction, I want you to remember this golden rule of our master blueprint. Centralize your checks in internal helpers so modifiers remain thin and testable. Pushing the actual logic down into those internal helpers, that's exactly what separates amateur code from production-grade, highly optimized smart contracts. You guys have built an incredibly solid foundation here in the applied Solidity development track. These concrete results perfectly set up our next step, which is rigorous testing. In the next lesson, we're going to systematically test and harden this exact integration to ensure it can survive the harsh, wild environment of a live blockchain.
But before we sign off, I want to leave you with a provocative question to ponder. If you switch your pause control from owner-only to a delegated role, how does that shift your system's overall vulnerability surface? It's a fantastic thought exercise to chew on. I highly encourage you to visit forge.college to dive deeper into this subject, explore our comprehensive testing modules, and check out the other incredible Web3 learning programs we offer. Thanks for tuning into this Forge College Explainer, and until next time, keep your code clean and your modifiers thin.